Hello, welcome to Lecture 6 of Circuits 1. As usual, today we'll start out with a little bit of review. I want to recap the equations governing parallel and series resistance combinations. After that, I will spend the bulk of the lecture talking about examples of circuit reduction. I think the best way to learn how to do this is just to see it being done, identify different combinations of parallel and series circuit elements, see how to go about an analysis approach. Towards the end, I'll try to do a practical application in which we use a voltage divider to perform a temperature measurement. Related educational material, circuit reduction stuff, is in section 1.5, and lab assignment number 2 will have more details about this temperature measurement application. Quick review of series resistor combinations and voltage division. If I have some series combination of resistors which are powered by some voltage source V sub S, the current I through all of these resistors is identical. They are in series. If I do KCL between any two resistors, I will find out that the current through resistor R1 is the same as the current through resistor R2, which is the same as all the other currents up to R sub n. It turns out that I can replace this series combination with a single equivalent resistance Req. If I choose this Req correctly, the voltage source will not be able to tell the difference between this single equivalent resistance and this series combination of resistances. It will deliver the same current. Its power delivery will be identical. The equivalent resistance that we use here is simply the sum of the individual resistances in this series combination. Just add them up. Now, once we've done this, we can also use a voltage divider formula to find the voltage drop across any individual resistance. For example, if I'm interested in the voltage drop across the resistor R sub K, the voltage drop across that resistor V sub K is just the total voltage drop across this combination divided by the equivalent resistance and multiplied by this individual resistance. So what I'm doing is essentially taking the percentage of the resistance that RK is to the total resistance and multiplying that by the total voltage drop to get the individual voltage difference across that resistor. Parallel combinations of resistors are as shown. I have a current source here. These resistors are in parallel. They all share the same voltage drop V. If I do KVL around any of these loops, I will find that each of these resistors has the same voltage drop. Since they have the same voltage drop, by definition, they are in parallel. In this case, I can also replace this combination of parallel resistances with a single equivalent resistance. I can place that resistance in series with the source. I will get the same voltage drop across this resistance that I get across any of these individual resistors. The voltage drop hasn't changed. The source can't tell the difference between this circuit and this circuit. For equivalent resistances of parallel combinations, you invert each of the individual resistances. Add those up and then invert the result. As we mentioned last time, we're actually working with something called conductance. Conductance is the inverse of resistance. So I add up all the conductances of these individual resistors. That gives me the conductance of the total overall parallel combination. 1 over that total combination conductance gives me the equivalent resistance. I can also use a current divider formula to find the current through any individual resistor in this combination. That equation is that the individual current is the total current into this combination times the equivalent resistance divided by this individual resistance. We've kind of inverted our previous voltage divider relationship. Now, whenever engineers generate a number, a result, it's a good idea to be able to check it against your gut instinct or your intuition about what that should be. Now, if you calculate a series resistance, that's kind of easy. you know that you're going to come up with an overall equivalent resistance that's higher than any of the individual resistances. You're adding up a bunch of resistances. Parallel resistances are not as intuitive to double check, but there are still some possibilities here. The equivalent resistance of a parallel combination is going to be less than the smallest resistance in that combination. As I combine resistors in parallel, the overall resistance of that parallel network goes down. In fact, it lies between a fairly wide range, but it gives you an option for checking things. The equivalent resistance is going to be less than the minimum resistance or the lowest resistance in the network, but it will be greater than or equal to that lowest resistance divided by the total number of resistors. So when you calculate a parallel resistance, at least take a quick look at it, double check, make sure you didn't forget to invert something or do something silly that's leading you to a wrong result. Now I want to revisit a couple of examples that we did previously, but using some shortcut methods provided by circuit reduction techniques. We had talked already about non-ideal power sources. They were used to do some limiting of power delivery to a load. We loaded them and we looked at the power output of the non-ideal sources, and we found out that we liked what we saw. However, that analysis method was a little tortuous. It took us a while to do. It turns out that it's actually extremely easy if you take advantage of circuit reduction techniques. This is our old loaded voltage source. Remember, our non-ideal voltage source consists of an ideal voltage source in series with a source resistance. We then added a load resistor to that, and we were looking for the load voltage. Once we found the load voltage, we could get the power delivery by the voltage squared over R. Well, all of these elements are in series. If we're looking for a specific voltage in that series combination, we can use a voltage divider formula. So V load is simply the total voltage across this combination times the ratio of R load to the combination of R load and RS. So by inspection, without doing any additional analysis, we can just claim that V load is this voltage times R load over R load plus RS. Took us a while to get to that result before. Our loaded current source looks like a parallel combination of stuff. Okay? I have a current source in parallel with a source resistance, which forms my non-ideal current source. I then add a load to that combination. I have a current source with a parallel combination of resistors. We wanted to find the current through R load. Once we found that current, we could use it to determine the power delivered by the non-ideal current source. Well, this is just a current divider. A current divider, if I want I load is the total current into the parallel combination times the other resistance in the parallel combination, so it's going to be IS times R sub S, over the sum of these two resistances. So I load is the total current times this resistance over the sum of this resistance plus this resistance. We can write that by inspection of this circuit rather than by writing KVL, KCL, Ohm's law, etc., etc. Now I just want to do a few examples of circuit reduction applied to circuit analysis. What I'm going to do is take a fairly general circuit, take series and parallel combinations of circuit elements within those circuits, combine those, and convert the circuit into a simpler equivalent circuit. The simplified circuit, quite often, I can analyze more easily than the original circuit and still find out what I need to know. This is not always possible, but when it works, it's great. Our first example is this circuit network. I'd like you to take a couple of minutes, pause the video, see if you can identify parallel and series elements, see if you can reduce the circuit, then come back and you can watch me do it. What I want is to take this network and determine simply an equivalent resistance as seen by anything that I hook up to these terminals. Okay, I want to combine these resistors so that they become a single resistance with the same resistance as seen from these terminals here. So I'm going to look for parallel and series combinations. These two resistors here look like they're in parallel. They share the same voltage drop. If I did KVL around this little loop, I'd find out that the voltage across this one is the same as the voltage across this one. Nothing else about this circuit leaps out at me as being in series or parallel, so I'll go ahead and combine these two. Then I'll add that equivalent resistance back in there and see what other simplifications I can do. So if I take a look at this combination, 6 ohms and 12 ohms, the equivalent resistance of a parallel combination of two resistors. Two resistors, as you recall, were a special case. I can multiply these two resistances together and divide by the sum of the resistances. So the equivalent resistance of this particular combination can be determined as 6 ohms times 12 ohms over 6 ohms plus 12 ohms. So this becomes 6 times 12. 12 is 2 times 6, so this becomes 6 times 3. So that becomes 4 ohms overall. I can take these two resistors and replace them with a single 4 ohm resistor. I'm going to redraw the circuit because that will help me identify other combinations of series and parallel resistances. So now this circuit becomes a 6 ohm resistor. I determined that the equivalent resistance of these two was 4 ohms, and then I have a 2 ohm resistor. Now I can identify that this 4 ohm resistance is in series with this 2 ohm resistance. Neither of these individually can be identified as being in series with the 2 ohm resistor, but once I've simplified it, then I can combine these two. Series resistances just add directly, so this circuit can become this 6 ohm resistance. 4 plus 2 is another 6 ohms. So I've combined these two into a single resistance. My circuit now looks like this. Now this becomes a parallel combination of resistors, both of which are 6 ohms. Just redrawing the circuit from here up to here. Now we're finally down to determining our overall equivalent resistance. So Req, again, parallel combinations of two resistances. I can multiply these together and divide by the sum. I get 6 ohms times 6 ohms over 6 ohms plus 6 ohms, which is 36 over 12, or 3 ohms. So this equivalent resistance is 3 ohms. Okay, example 2. I want to find V out, the voltage, across this parallel combination of two current sources and two resistors. What I'm going to do is combine these two current sources into a single current source, then determine the equivalent resistance of these two resistors. From that, I can determine the voltage across this. I suggest that you pause the video, try that for yourself, see how the process works. Then when you come back, I'll do it for you. The first thing I'm going to do is combine these two current sources. The overall effect of these is to put 2 amps into this upper node with one current source and take 1 amp out with the other current source. So those two combine into a single current source which puts 1 amp into the upper node. That can then be placed into a parallel combination of the 9 ohm resistor and the 6 ohm resistor. For the special case of two parallel resistances, I can determine the equivalent resistance by multiplying the resistances together and dividing by the sum of the resistances. So Req is 9 ohms times 6 ohms over 9 ohms plus 6 ohms. So this is 9 times 6 over 9 plus 6 is 15, which can be factored into 3 times 5. I can cancel that with that, and I get an equivalent resistance of 18/5 of an ohm. So now this circuit can be rewritten as a 1 amp source going into a resistance, which is 18/5 ohms. And I can now determine the voltage drop across this equivalent resistance using Ohm's law. This is still V out. Okay, since they're all in parallel, my V out is still the voltage across any one of these elements, or equivalently, the voltage across the parallel combination of them. So V out by Ohm's law is just 1 amp times 18/5 ohms, which is 18/5 volts. And that's 3.6 volts. Let's try a slightly more complicated example now. In this circuit, I want to find I1, which is the current through the 9 ohm resistor, V sub S, the voltage across the 6 amp source, and VO, which is the voltage across the 2 ohm resistor. Now my general solution strategy that I'm going to suggest for this one is that if I can find V sub S, I've found one of the main things that I'm looking for, first of all. Secondly, V sub S gives me I1 almost directly. I will now know the voltage drop across this 9 ohm resistor. Ohm's law will directly tell me the current through that resistor. After I've got that, I can worry about V sub O a little bit later. Give this example problem a try. Come back and watch me do it. Okay, this 1 ohm resistance and this 5 ohm resistance are in series. Okay, KCL tells me that the current through here is the current through there. I can combine those into a single equivalent resistance directly, which has a resistance of 1 plus 5, which is 6 ohms. Then I have a 6 ohm resistor in parallel with this 2 ohm resistor. So let me reduce this section of this circuit as follows to be this 2 ohm resistor in parallel with the 6 ohms, which is the series combination of 5 ohms and 1 ohm. The equivalent resistance of a parallel combination of two resistances is the product of the resistances divided by the sum of the resistance. So the equivalent resistance of these two resistors is 2 ohms times 6 ohms over 2 ohms plus 6 ohms, or 12 ohms divided by 8 ohms. 12 over 8 is 1.5 ohms. So now I'm going to substitute a single 1.5 ohm resistor in for these guys and then continue on with my circuit simplification. I'll go on to the next slide to do that. Okay, now I've replaced that network of 3 resistors on the previous slide with an equivalent 1.5 ohm resistor. I can now continue to simplify this circuit. This 3 ohm resistance in series with this 1.5 ohm resistance is an equivalent resistance of 4.5 ohms. I just add the resistors if they're in series. So this circuit becomes a 6 amp source with a 9 ohm resistor in parallel with a 3 plus 1.5 ohm resistor, or a 4.5 ohm resistance. Again, we have a parallel combination of 2 resistors. I can take the product of the resistances, divide that by the sum of the resistance to get the equivalent resistance. So Req is 9 ohms times 4.5 ohms over 9 ohms plus 4.5 ohms, which becomes 9 times 4.5 over 3 times 4.5, or 3 ohms. Now I can rewrite this circuit as a 6 amp source going into a single equivalent 3 ohm resistor. I can determine V sub S directly from Ohm's law by multiplying the resistance times the current. So V sub S is 3 times 6, which is 18 volts. Now that we know that V sub S is 18 volts, I'll go to the next slide. We'll continue to find the rest of the things that we need to know about this problem. Okay, now this is now equivalent to our previous circuit. My voltage across my source is 18 volts as far as the rest of this network knows. I just have 18 volts across these two terminals. I need to determine now I1 and V0. I know the voltage difference across this 9 ohm resistor, so I1 is directly determined by Ohm's law to be 18 volts over 9 ohms, which is 2 amps. Now I can determine VO from my previous circuit. If you recall, I simplified this entire network down to a 1.5 ohm resistor. Okay. I have an 18 volt difference between here and here. This 3 ohm resistor and this equivalent 1.5 ohm resistor will now form a voltage divider. Let me redraw the circuit to illustrate what I'm saying. So I can redraw this circuit as an 18 volt source with a 3 ohm resistor and an equivalent 1.5 ohm resistor. I'm applying an 18 volt difference across here. This resistor doesn't really matter. This can become a voltage divider. VO here is the total voltage, 18 volts, times this resistance divided by the sum of these resistances. So VO is 18 volts times 1.5 ohms over 3 ohms plus 1.5 ohms. So this is 18 over 3, which is 6 volts. And one last example. For this circuit, I want to first determine the equivalent resistance seen by the source. So I'm going to take these terminals here, look into those, and simplify this network to determine an equivalent resistance. After I do that, I want to find currents I1 and I2, where I1 is defined as the current out of the 6 volt source, I2 is the current through the 3 ohm resistor. Take a shot at doing that, come back and watch me doing it. My first step is to determine an equivalent resistance for this overall resistive network as seen by these terminals here. These two resistors form a series combination. I've been slightly misleading on purpose here to set them up so that they kind of look at first glance as if they're in parallel, right? They're set up to look in parallel. However, if you take KCL here, you'll see that whatever current is going through this resistor is also going through that resistor. On the other hand, if you do KVL around this loop, the voltage difference between here and here says that the voltage across this resistor is not the same as the voltage across this resistor. These resistors are in series, not in parallel. After having identified those as being in series, I can combine those into a single 6 ohm resistor. So I have a 3 ohm resistor that I haven't touched. I have this 6 ohm resistor that I haven't touched. And I have this equivalent 6 ohm resistance. Now I can determine the equivalent resistance here as follows. Remember, the equivalent resistance of a set of parallel resistors is 1 over the sum of the conductances. So I have 1 over 3 ohms plus 1 over 6 ohms plus 1 over 6 ohms. I can also do this problem by successively combining pairs of resistors. A 6 ohm resistor in parallel with a 6 ohm resistor is going to simplify down to a single 3 ohm resistor. A 3 ohm resistor in parallel with a 3 ohm resistor will simplify down to a single 1.5 ohm resistor. So this equivalent resistance should turn out to be 1.5 ohms. So now I found the equivalent resistance that I want out of this circuit. I next need to determine the current out of the source. I'm going to leave this little section here because I'll want it later. The current out of the source, I1, and the current through this 3 ohm resistor, I2. I1 is simple. I can take this circuit, plus minus 6 volts, combining these two. I already said my equivalent resistance was 1.5 ohms, so I1 is simply by Ohm's law 6 volts over 1.5 ohms, or I1 is equal to 4 amps. Now, if I know I1 is 4 amps, I can use this intermediate step in order to find I2, right? Because I've simplified this whole network down into this 3 ohm resistor. I have I1 going in here. I no longer care what kind of source this is. This now looks like a current divider. So I2 is equal to I1 times the other resistance, 3 ohms, over the sum of the two resistances that are in parallel. So this becomes 1/2 I1, which is 1/2 of 4 amps, which is just 2 amps.